Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Sciences, SOS, Bachelor's degree programs. Bachelor of Science, BSc. Elective. Chemistry, English. Ch01 Atoms and Molecules. Block-1 Structure of Matter, I. Unit-1 Old Quantum Theory. 1.1 Introduction. The ideas of classical mechanics developed by Galileo, Kepler and Newton, when applied to atomic and molecular systems, were found to be inadequate. Need was felt for a theory to describe, correlate and predict the behavior of the subatomic particles. The quantum theory, proposed by Max Planck and applied by Einstein and Bohr to explain different aspects of behavior of matter, is an important milestone in the formulation of the modern concept of atom. In this unit, we will study how black body radiation, heat capacity variation, photoelectric effect and atomic spectra of hydrogen can be explained on the basis of theories proposed by Max Planck, Einstein and Bohr. They based their theories on the postulate that all interactions between matter and radiation occur in terms of definite packets of energy, known as quanta. Their ideas, when extended further, led to the evolution of wave mechanics, which shows the dual nature of matter and energy. Objectives. After studying this unit, you should be able to describe the discovery of electron, proton and neutron. Explain the atom models of Thomson and Rutherford. List the wave parameters of light. Describe the shortcomings of classical physics. State Planck's theory and explain its application to black body radiation and heat capacity variation. Define photoelectric effect and explain it in the light of Einstein's theory. List Bohr's postulates and derive an expression useful in calculating the radius of the hydrogen atom. Explain the atomic spectra of hydrogen in the light of Bohr's theory. Analyze critically the advantages and limitations of Bohr's theory, and state the refinements in the atomic spectra theory. 1.2 Discovery of subatomic particles. The atomic theory of the Greek philosophers, Leucippus and Democritus, 400 BC, held that continued subdivision of matter would ultimately yield atoms which would not be further divided. The word atom is derived from the Greek word aromos, which means uncut or indivisible. Dalton, 1808, based his atomic theory on the ideas of Democritus and was able to explain the laws of chemical combination. Toward the end of 19th century, it began to appear that the atom itself might be composed of even smaller particles. This discovery was brought about by experiments with electricity. Attempts to pass a high-voltage electric current through gases under reduced pressure led to Julius Plucker's discovery, 1859, of cathode rays, Fig. 1.1. The cathode rays stream from the negative electrode, which is called the cathode. These rays consist of negatively charged particles which travel in straight lines. The cathode rays give off flashes of light when they strike a screen coated with substances like zinc sulfide. The picture tubes in television sets and computer monitors function on this principle. The particles in cathode rays were later called electrons, as suggested by Stoney. The determination of charge to mass ratio of electrons by Thomson, 1897, confirmed the fact that the electrons, which originate from the metal of which the cathode is constituted, are the same no matter what metal is employed as the cathode. In other words, electrons are fundamental particles of all types of matter. If one or more electrons are removed from a neutral atom or molecule, the residual entity is positively charged. During the formation of cathode rays in an electric discharge tube, one or more electrons are removed from each of the atoms, and the positive particles so produced move toward the negative electrode. If this electrode has holes in it, the positive ions pass through them. These streams of positive ions, called positive rays, were first observed by Goldstein, 1886. The charge-to-mass ratios of positive ions depend on the nature of gases taken in the discharge tube. For example, charge-to-mass ratios for the positive rays obtained from hydrogen and neon are not the same. You can compare this fact with the earlier statement that the charge-to-mass ratio value of electrons is the same, irrespective of the nature of gases kept in the discharge tube. The positive particles produced when hydrogen is taken in the discharge tube are called protons in accordance with the suggestion of Rutherford, 1920. In Greek, prots means first. The protons, like electrons, are assumed to be constituents of all atoms. The proton has a positive charge, although equal in magnitude to that of the electron. In the same year, Rutherford suggested that there might exist particles which he called neutrons, having a mass equivalent to a proton but without charge. Chadwick, 1932, discovered neutrons during his experiments on the bombardment of beryllium by A particles. The properties of electron, proton and neutron are summarized in Table 1.1. Although other subatomic particles have also been identified, atomic structure is adequately explained on the basis of the number of electrons, protons and neutrons in an atom. Table 1.1, Subatomic particles. Look at the screen. Along with discoveries of subatomic particles, various theories were put forward to explain the structure of the atom. As mentioned in the last section, Dalton proposed a theory that atom is indivisible. But the discovery of subatomic particles like electron led to a revision of this theory. Thomson, 1904, proposed a model for the atomic structure, known as plum pudding model, which is pictorially described in Fig. 1.3. He considered an atom to be a uniform sphere of positive electricity of about low 4 cm radius, with the electrons embedded in such a way as to give the most stable electrostatic arrangement. This model was not able to explain the observation of Geiger and Marsden, 1909, regarding the scattering of the A particles directed towards thin gold foil. Some were deflected from their straight line path and a few recoiled back toward their source. Fig. 1.4, a uniform sphere of positive charge, would mean only a gradual deflection of the A particle, but not scattering as it progressed through the foil. Look at the screen. Thomson compared atom to a pudding with partially dried grapes in it. Rutherford, on observing the recoil of some alpha particles from that gold foil, exclaimed, "It was quite the most incredible event that has ever happened to me in my life. It was almost as if you fired a 15-inch shell into a piece of tissue paper and it came back and hit you. If a nucleus of an atom were the SLZE of a tennis ball, the atom, A, would have a diameter of over." Rutherford, 1911, on the basis of the alpha-ray scattering experiment, suggested that positive charge and mass of the atom are concentrated in a space which is very much smaller than that occupied by the atom as a whole. He suggested an atomic model, known as Euclidean model, which consisted of a nucleus at the center and negative particles surrounding it. The nucleus accounted for mass and positive charge. To support the fact that the electrons did not fall into a nucleus as a result of electrostatic attraction, Rutherford found it necessary to postulate rapid rotation of the electrons. The nucleus, just as planets go around the Sun. This analogy is misleading since, according to classical electromagnetic theory, an electron in orbit is subject to continual acceleration towards the center, and the accelerated electric charge must emit radiation. The consequent loss of energy should bring the electron down in a spiral path to the nucleus, that is the collapse of the atom. Within 2 years, Niels Bohr suggested a better theory of the atom. Before studying Bohr's theory, let us analyze the wave properties of light and the reason for the failure of classical physics in describing the properties of subatomic particles like electrons. 1.4 Light as electromagnetic wave. A beam of light has oscillating electric and magnetic fields associated with it. It is characterized by the properties such as frequency, wavelength and wave number. We can understand all these properties by considering, in general, a wave propagating in one dimension only. Fig. 1.5, along Abgdefki. Figure 1.5 Wave propagation. Electromagnetic theory of light depicts the propagation of light through space as oscillating electric and magnetic fields. These fields are mutually perpendicular and also perpendicular to the direction of propagation of light. Further, the energy of a wave depends on the square of its amplitude. Wavelength lambda, Greek, lambda, is the distance between two successive crests or troughs. The length BF or DH in Fig 1.5 is equal to the wavelength, and it is expressed in the unit meter, m. The frequency is the number of waves per second. It is represented by the Greek letter V, nu. Its unit is hertz, hertz. In fact, 1 hertz is equal to second powers minus 1, s powers minus 1. Wavelength and frequency are related by the expression 1.1, where c is the velocity of the light wave in the medium. Lambda is equal to c upon v. In vacuum, c is equal to 2.998 x 10 powers 8 m s powers minus 1, and we use this value for c in our calculations. From the above expression, we understand that wavelength is inversely proportional to frequency. The reciprocal of frequency is the period of oscillation, t is equal to 1 upon v. It indicates the time for one oscillation. Similarly, the reciprocal of wavelength is the wave number, v bar, nu, tilde. Wave number is related to frequency and wavelength as per EQ. 1.2. V bar is equal to 1 upon lambda is equal to V upon C dot 1.2. The SI unit of V bar is m power minus 1, although most of the literature values are in cm power minus 1. The peak height kilobyte or mf, or trough depth, LD or NH, is called the amplitude of the wave. In section 1.6, we shall see how energy of a light wave is related to its frequency and wavelength. The electromagnetic spectrum describes the range of values of frequency and wavelength in electromagnetic radiation. The characteristics of the electromagnetic spectrum are given in Table 1.2. Look at the screen. At one end of the spectrum, there are X-rays and gamma rays with low wavelength and high frequency. At the other end, we find radio waves and microwaves with high Wavelength and low frequency. In Table 1.3 you can find the wavelength values of ultraviolet and visible light of different colors. Color and wavelength in M. Ultraviolet 200. Violet 410. Indigo 430. Blue 470. Green 520. Yellow 570. Orange 620. Red 710. 1.5 Failures of classical physics. The laws of motion put forward by Newton are the pillars of classical mechanics. Till 1900, it was thought that these classical concepts and laws hold good both for celestial bodies like planets and subatomic entities like electrons. Is this assumption quite acceptable? Is it advisable to use a Lorry weighbridge to find the weight of a safety pin? Before trying to see whether classical mechanics is applicable to subatomic system, we have to be familiar with important assumptions of classical mechanics, viz. No restriction on the value that a dynamic variable, e.g., energy, momentum, etc., can have. 2. No limit to the accuracy with which one or more of the dynamic variables of a system can be measured except the limit imposed by the precision of the measuring instruments. 3. No restriction on the number of dynamic variables that can be accurately measured at the same time. Added to classical mechanics, other tools in the bag of classical physics were thermodynamics, optics, and electromagnetic theory. A number of experiments done in the latter half of the 19th century and the first 2 decades of the present century gave results totally at variance with the predictions of classical physics. Let us now consider 4 specific cases given below, which indicated the inadequacy of classical physics. I. Black body radiation. 3. Photoelectric effect. 2. Heat capacity variation. 4. Atomic spectra. As a first case, we shall take up black body radiation. 1st May 2001 Black body radiation. Black body radiation is the radiation emitted by a non-reflecting solid body. A perfect black body is one which absorbs SLL, the radiation falling on it. Experimentally, a hollow body, blackened on the inside and with a small opening, is considered a typical black body. Any radiation that enters through the small opening is reflected repeatedly from the walls until all of the energy eventually becomes absorbed. Fig. 1.6a. A Mach body is both a good absorber and radiator of energy. Of the various types of bodies heated to particular temperature, only black body radiates the maximum amount of energy. It radiates the same amount of energy as it absorbs. Look at the screen. The main aspects of black body radiation which emerge from experimental observations are old quantum theory. At shorter wavelength region, that is at higher frequency region, intensity of radiation is low. 2. At every temperature, there is a wavelength at which energy radiated is maximum. This wavelength is called a value of that temperature. 3. At higher temperatures, there is increased intensity of radiation in the shorter wavelength region. These facts are pictorially represented in Fig. 1.6b. A piece of iron, say at 375 K, is hot for the hand to touch but no visible radiation, i.e., shorter wavelength radiation, is emitted by the metal. However, with increase of temperature, it becomes progressively dull red, bright red, orange, yellow and white hot. In general, as temperature is increased, the radiation emitted contains more of shorter wavelength region, whether it is from black body or an iron piece. In contrast to the above experimental fact, the classical theory predicts that the black body ought to radiate over the whole wavelength region including visible region even at room temperature. As temperature is increased, the radiation emitted should get uniformly more intense. In other words, an iron piece even at room temperature should radiate a little in the visible range. When the evidence of eyes and fingers does not fit the predictions of the classical theory, it is time for this theory to be modified. In section 1.6, we shall see how quantum theory successfully explains the experimental facts regarding black body radiation. 1st May 2002 heat capacity variation. The second drawback of classical physics is its inadequacy in explaining heat capacity variation with temperature. Dulong and Pathit, based on experimental evidence then available, proposed that the molar heat capacity at constant volume for metals must be equal to 24.93 J mol K, irrespective of temperature. Molar heat capacity is the quantity of heat required to raise the temperature of 1 mole of a substance through 1 degree Kelvin. Anyhow, the experiments performed at low temperatures reveal significant deviation from Dulong and Pathit law. All metals are found to have molar heat capacities lower than 24.93 J mol K at low temperatures, and the values appear to approach zero as temperature chosen is near absolute zero. In section 1.6, we shall see how quantum theory explains heat capacity variation with temperature. 1st May 2003 photoelectric effect. Let us now take up the third major setback to classical theory. The emission of electrons when metals are irradiated with ultraviolet light is known as photoelectric effect. This was observed by Hertz in 1887. The electrons, so emitted, are known as photoelectrons, to differentiate them from the electrons remaining inside the metal atoms. The main feature of this phenomenon is that a minimum frequency of light, known as threshold frequency, U, is required to emit photoelectrons. If the frequency of the incident light is less than this value, then photoelectrons are not emitted. The value of U is a characteristic of the metallic surface used. Increasing the frequency of the light beyond threshold frequency value only increases the velocity of the photoelectrons. These observations could not be explained by the 19th century view of light as wave phenomenon. In section 1.7, we shall see how Einstein's theory explains the experimental facts concerning the photoelectric effect. 1st May 2004 atomic spectra. The fourth front, where again classical theory failed, is the atomic spectra. Let us first understand what atomic spectrum is. When gases or vapors of a chemical substance are heated in an electric arc or Bunsen flame, light is emitted. If a ray of this light is passed through a prism, a line spectrum is produced. Fig. 1.7. This spectrum consists of a limited number of colored lines, each of which corresponds to different wavelength of light. The line spectrum of each element is unique. On careful examination, it was found that in the atomic spectra of elements, spectral lines occur discretely at lower frequencies followed by a continuous spectrum at very high frequencies. An examination of a part of the spectrum of hydrogen as in Fig. 1.8a indicates the prism of three groups of lines. One of them is in the visible region, and it was discovered by Balmer in 1885, Fig. 1.8b. This series, known as Rollmer series, has a mathematical relationship as shown by EQ 1.3. In the case of atoms, only electronic transitions are possible and therefore, the spectrum is very simple, consisting of electronic spectral lines. In the case of molecules, on the other hand, besides electronic transitions, transitions between rotational and vibrational energy levels are also possible, and therefore molecular spectrum is relatively complex and has a large number of closely spaced lines and looks like a band, called band. Look at the screen. 1.6. Planck's quantum theory, black body, radiation and heat capacity variation. Old quantum theory. The quantum theory, proposed by Max Planck in 1900, is the result of the realization that the failure of classical physics is due to the wrong assumption that the energy of the system may take any arbitrary value. He suggested a detailed model for the processes taking place at the cavity walls. He considered the black body to consist of oscillators of molecular dimensions, each with a fundamental vibration frequency V, and that each oscillator could emit energy only by a specified amount, known as quanta, but not continuously. 1.7. Einstein's theory of photoelectric effect. Applying the photon concept to the photoelectric effect, Einstein proposed that an electron at the surface of the metal gains an energy hv by the absorption of a photon from the electromagnetic radiation, if the frequency v of the photon is greater than the minimum value Vo, called threshold frequency, which is characteristic of a particular metal, then the emission of photoelectron occurs. The difference, hv, is transformed as the kinetic energy of the photoelectron, which is equal to m0. In conformity with the principle of conservation of energy, Einstein's theory can be stated as hv is equal to m0. 1.8. In this expression, V and Vo are the photon and threshold frequencies, respectively, while m and v are E the mass and velocity of the photoelectron. If v, Vo, then m0 is negative, which is meaningless. That is, photoelectron emission does not take place. WHEMV is less than VO. 1. 8. Bohr atom model. The quantum theory was applied by the Danish physicist Niels Bohr, 1913, to explain the spectrum of hydrogen atom. He suggested an atom model which is an improvement over Rutherford model described in section 1.3. Bohr based his theory on the following postulates. An electron can exist only in orbits of definite angular momentum and energy. Each orbit is known as a stationary state. 2. The electron does not radiate energy when it is in an allowed orbit. 3. While in an orbit, the angular momentum of the electron, mvr, is an integral multiple of h2 units. mvr is equal to nh upon 2 pi, where m and v stand for the mass and velocity of the electron, r is the orbit radius, and n is an integer called principal quantum number. The orbits are called k, l, m, n, depending on the values of n, with 1, 2, 3, 4. At the time this view was proposed, there was no reason for the quantization of angular 1885 to 1962 momentum. Anyhow, in section 1.6 you saw how h has the units of angular momentum. 4. Each spectral line is produced by a single electron. When an electron jumps from one orbit to another, radiation of a definite frequency is emitted or absorbed, giving rise to a definite spectral line. The frequency of the spectral line is related to the difference in energy, del-E, between initial and final levels, as per the equation. Delta E is equal to HV is equal to hc/Ber. Using the above postulates, he was able to calculate the radius of different orbits in hydrogen atom, the energy of the electron in its orbits and the frequency of the spectral lines. 1.9 Calculation of radius of orbits. Bohr atom model considers an electron of charge E and mass m revolving round the nucleus of charge positive Ze with velocity in a stationary orbit of radius r. Fig. 1.9. The nuclear charge is taken as positive Ze since the nucleus is assumed to contain Z protons and each proton has charge positive E. For attaining mechanical stability, the electrostatic force of attraction, F A, between the electron and the nucleus, must be equal to the centrifugal force, Fe, which is operating in the opposite direction. 1.12 Critical analysis of Bohr's theory. Note that U1e spacing between two successive levels becomes smaller as n increases. We have mentioned about the converging nature of energy levels in section 1.10 also. Experimentally, it has been found that within a particular series, for example, Lyman series, the lines in the spectrum of atomic hydrogen are discrete at lower frequencies, and they converge as the frequency increases. Each successive line becomes closer to the previous one. This is quite evident from the spacings of the first four lines I tilde. Lyman series, as entered in the last column of Table 1.6. Table 1.6, Wove number of dues in Lyman SCDES. Number of AI is equal to 1.097 x log 7, 4, spacing. The spectral, G, 2m, I, 2, G, tilde, in tilde. Line, A, 1128.228 x log 6. 2I 39.751 x log 6 1.523 x log 6. 314I.02 TRX 107.5.29 XI at 4151.053 x log 7 2.5 x 105. As EQ 1.26 predicts, each series of lines converges towards a limit beyond which the spectrum is continuous. At this point, electron responsible for the spectral line has been excited into an orbit of such high energy, N2 is equal to W, that it has effectively escaped from the influence of the nucleus. In other words, the atom has lost its electron and formed a positive ion, H, G, dash 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 plus H, E, plus E. The energy difference between the GMND state of hydrogen atom and the excited state that corresponds to convergence limit of the spectral lines, N2 is equal to W, is called the ionization energy of hydrogen atom. Note that ionization energies refer to the removal of an electron in the gas phase. We will study more about ionization energies in section 1.12 and in Unit 3. Thus, Bohr's theory can explain the appearance of discrete spectral lines at lower frequencies and a continuous spectra at higher frequencies in the atomic spectra of hydrogen. In the light of what you have studied above, answer the following Suck 7. What is the reason for the increase in the spectral frequency as N2 increases? Let us examine how the theoretical model of Bohr is able to explain some of the features given below. Atomic spectra of hydrogen. Rydberg constant value. Ionization energy of hydrogen. Prediction of new elements. Bohr's theory is successful as an atom model to the extent that its findings are consistent with atomic spectra of hydrogen. The agreement between the theoretical and experimental values of spectral frequencies is a testimony to the validity of this theory. Again, the value of Rydberg constant, calculated according to Bohr's theory, is in agreement with the experimental value. The ionization energy of hydrogen atom 15 defined as the minimum energy necessary to remove the electron from n is equal to 1 state to infinite distance, n2 is equal to alpha, leaving it without any kinetic energy, and it can be calculated using EQ 1.28 for the hydrogen atom, the ionization energy in the wave number unit. For the purposes of chemical calculation, ionization energy of hydrogen may be defined as the energy required to remove 1 mole of electrons, i.e., 6.022 x 10 electrons from 1 mole of hydrogen atoms in the ground state. Hence, ionization energy. Thus Bohr's theory offers a method of calculating ionization energy of hydrogen and this principle has been extended to other elements in calculating their ionization energies. From spectral studies, Bohr constructed a theoretical periodic chart which agreed with Mendeleev's chart. On the basis of atomic spectra, Bohr was able to predict that the element with Z is equal to 72 has properties similar to titanium, 2 is equal to 22, and zirconium, 2 is equal to 40, and this element was later discovered and named hafnium. Limitations of Bohr's theory. According to Bohr's theory, angular momentum tilde if the electron on never be zero. However, later on, wave mechanics, Unit-2, shows that in n is equal to j state, dectron has zero angular momentum. The hyperfine structure in the atomic spectra of hydrogen is not well explained by Bohr's theory. Also, Bohr's theory is not able to explain the spectra of multi-electron atoms. Further, this theory does not explain how molecules are formed from atoms. It does not recognize the wave properties of electrons. Just like electromagnetic radiation, the electron also has both particle and wave aspects. Using the crystal spacings in a nickel crystal as a diffraction grating, it is possible to obtain diffraction patterns that could be understood in terms of wave motion of the electron. But Bohr's theory has not provided any explanation for this phenomenon. According to Bohr's theory, electron moves in orbits known as stationary states. The path of this orbit, or its trajectory, can be known only if we know simultaneously both the position and the velocity of electron. It, therefore, assumes the accurate and simultaneous determination of both position and velocity of the electron. But this assumption is not in conformity with the wave nature of electron. In the next unit, we shall see how theories were developed by Heisenberg and Schrödinger to explain the wave characteristics of electrons. 1.13 Refinements in atomic spectra. Theory. Sommerfeld, 1916, modified Bohr's theory and tried to interpret the fine structure in the three-atomic spectra of hydrogen as due to elliptical path of the electron. He introduced another quantum number, known as azimuthal quantum number, which was by later modifications represented as I, and shown to have values 0, 1, n-1, where n is the principal quantum number. Thus if n is equal to 2, then one can have values 0 and 1. the splitting of spectral lines when atoms are placed in a strong magnetic field, known as Zeeman effect, could also be partially explained by introducing magnetic quantum number M1, describing the allowed orientations of electron orbits in space. It was shown that for each value of L, M1 can have 2L plus 1 values, namely from plus L to minus L. Hence, if L is equal to 1, ML can have 3 values, plus 1, 0 and 1. You will see in the next unit an alternate way of arriving at the quantum numbers N, L and ML. 1.14 Summary. In this unit, we have focused our attention on the developments leading to tilde or atom model. The instances and reasons for the failure of classical physics are given. Using quantum theory, Planck, Einstein and Bohr explained black body radiation, heat capacity variation, photoelectric effect and atomic spectra of hydrogen. But each of the above theories had limited success. No doubt these theories rejected the classical concept of the arbitrary energy values for an atomic system. But with regard to other major cracks in the classical theory, namely simultaneous and precise determination of position and momentum, no remedy has been suggested. This loophole was plugged by de Broglie, Heisenberg and Schrödinger, and we shall study in the next unit about their concepts, collectively known as wave mechanics. Since wave mechanics is based on new quantum postulates, the theories proposed by Planck, Einstein and Bohr are collectively called old quantum theory. Sorry, there are some topics missing in this audio. Kindly refer to link in description for the PDF. Thank you. Subscribe to our channel for more updates, and we will see you with the next chapter.